Welcome to AI Engineering Mastery, the ultimate series to help you become a next-gen AI engineer. I'm Sonu, and you're watching the very first episode of Season 1, where we dig deep into what AI engineering really is, why it matters, and how it sets itself apart from just machine learning or data science. Hit that subscribe button and enable notifications so you don't miss our Monday to Wednesday episodes. Trust me, you want to stick with this journey. You've probably built a machine learning model before. Maybe it predicts house prices, classifies images, or analyzes sentiment. That's exciting stuff. But here's a serious question. What happens after you've trained that model? You've got this great model in your notebook. But how do you get it out into the real world, into an app, a product, something users can actually benefit from? That's where AI engineering comes in. AI engineering is all about building real-world machine learning systems, reliable, scalable, and maintainable. You might also hear the term MLOps, short for Machine Learning Operations. It's a blend of ML, DevOps, and software engineering that ensures your models don't just live in Jupyter notebooks, they live in production. Think of it this way, training the model is maybe 10% of the total work in a real-world ML project. The other 90%, that's what AI engineers focus on. Let's break this down into simple stages. 1. Define the problem clearly. Before any code is written, you need to understand the why. What's the business or product goal? Are you trying to reduce churn? Automate support? Detect fraud? Clear problem framing guides everything that follows. 2. Prepare the data. Most of the time, real-world data is messy. You need to collect it, clean it, transform it, and validate it. And this isn't just a one-time job. You'll need reliable pipelines that do this consistently over time. 3. Train the model. This is the part most people focus on. You choose algorithms, train, validate, and tune them. But remember, this is just one piece of the puzzle. 4. Deploy the model. Now it's time to actually use your model. You might wrap it in an API, deploy it to a server, or integrate it into an application. You'll need tools like Docker, APIs, and cloud services to get it running in production. 5. Monitor and maintain. Your model is live, but that's not the end. You need to track performance over time. Is accuracy dropping? Is the data changing? Is latency acceptable? You'll set up systems to monitor for these issues and trigger retraining if needed. 6. Scale it. Let's normalize the amount column and drop the time column. Your model needs to grow with it. That means distributing the training, scaling the infrastructure, and managing load balancing. Separate features and labels. It's not just about building the system, it's about keeping it stable and responsive at scale. AI engineers often work with Python libraries like scikit-learn, TensorFlow, or PyTorch for building models, Docker for packaging, APIs for deployment, cloud platforms for scaling, tools like Kubernetes, C/CD pipelines, and monitoring dashboards for operations. You don't need to master all of them at once, but understanding how they fit into the bigger picture is key. Let's be real, building a model that works once in a notebook is cool, but building a system that works every day in the real world? That's valuable. That's impactful. That's AI engineering. It's the difference between building a prototype and building a product. If you want to be someone who makes ML work for real people, then AI engineering is a discipline worth investing in. It's one of the most in-demand skill sets right now, and for good reason. So here's the big takeaway. AI engineering is the bridge between data science and real-world applications. It's where your models stop being code and start being products. If you're serious about building ML systems that actually make a difference, understanding AI engineering is non-negotiable. From early theoretical ideas to the intelligent systems we see all around us today, AI has come a long way, and it's only just getting started. The concept of intelligent machines isn't new. Decades ago, researchers began imagining how machines could mimic the brain. They introduced the idea of artificial neurons, simple computational units that simulate how the brain processes information. This gave rise to neural networks, the foundation of many modern AI systems. At the same time, new ideas around learning through interaction, what we now call reinforcement learning, began to emerge. Machines could learn by trial and error, just like humans. For years, neural networks struggled to deliver, but eventually breakthroughs came. With better data, faster hardware, and smarter algorithms, deep learning was born, using neural networks with multiple layers to process complex patterns. We saw powerful models like convolutional neural networks, which revolutionized how machines see images, and recurrent neural networks, which allowed machines to understand sequences like speech or text. These architectures changed the game for computer vision, language processing, and more. Then came a turning point. Machines started learning to play games, not just following instructions, but teaching themselves how to win. They mastered video games from raw pixels. Then they took on some of the world's most complex games like chess and Go, and won against human champions. These were massive breakthroughs that proved AI could solve real-world problems without explicit programming. Next came a new wave of models that changed everything in natural language processing: transformers. These models don't just understand words, they understand context, intent, and nuance. They can translate languages, write essays, and even code. Their power comes from scale and training on vast amounts of text, allowing them to generalize across tasks and generate language that feels almost human. Today's large language models, chatbots, and content generators are all built on this revolutionary architecture. But AI isn't just about text. Generative AI now creates stunning visuals, music, and even video using advanced techniques like diffusion models. We've also entered the age of multimodal AI, systems that can process text, images, and actions at the same time. These models can chat, recognize objects, and even control robots, all from a single model. The boundaries of what's possible are expanding rapidly. Of course, building an AI model is only part of the story. The real challenge is getting it to work in the real world. That's where AI engineering, or MLOps, comes in, the practice of building pipelines, automating training, deploying models, and continuously monitoring them in production. From data collection to model deployment and performance tracking, this is where AI truly becomes impactful. The systems we rely on today, search engines, recommendation systems, voice assistants, exist because of these robust engineering practices. So, where do we go from here? We're moving toward AI that's more general, more human-like, and more deeply embedded in every part of life, from healthcare and education to creative industries and beyond. AI isn't just a tool anymore, it's becoming a collaborator. AI has come a long way, from simple neurons to billion-parameter models capable of incredible feats. And we're only at the beginning of what's possible. If you found this breakdown helpful, make sure to like the video, subscribe, and share it with someone curious about AI. Let me know in the comments, what part of AI history amazes you the most? You've probably come across titles like data scientist, machine learning engineer, and MLOps engineer. But what do these roles actually mean? Where do their responsibilities begin, and where do they overlap? Building an AI-powered solution isn't a one-person job. It's a multi-step journey, from identifying a business problem to training a model, deploying it, and keeping it running in production. Let's break down who does what. Let's start with the data scientist. Their main job? Turning messy business problems into structured machine learning tasks. They work closely with stakeholders to understand what needs to be solved. Then, they gather data, clean it, explore it, and make sense of it, looking for patterns, trends, or anomalies. Once the data is ready, they build and train models. This involves selecting algorithms, engineering features, and experimenting with different approaches to get the best performance. Think of them as the research and development team of AI. They typically work in environments like Jupyter Notebooks and use frameworks like scikit-learn, TensorFlow, or PyTorch. But here's the catch: they may not always think about how to take that model and run it in a live, user-facing system. That's where the next role comes in. An ML engineer takes the model built by the data scientist and turns it into a real product. Their focus is on building scalable, reliable systems that serve the model's predictions in real time or in batch mode, depending on the use case. This means packaging the model, integrating it into an application, and deploying it to production. They make sure it runs efficiently, handles high traffic, and stays healthy. ML engineers often come from a software engineering background, but with a deep understanding of machine learning concepts. They bridge the gap between experimentation and execution. They also handle retraining workflows, performance tuning, and often write the infrastructure code to support version control, testing, and scaling. Now comes MLOps, short for Machine Learning Operations. While it can be a distinct role, it's often seen as a discipline that ensures ML systems are not just built, but also continuously integrated, delivered, and monitored at scale. An ML ops engineer focuses on automation, setting up pipelines that automate data ingestion, model training, testing, deployment, and monitoring. They apply DevOps principles to the ML lifecycle. They also manage the infrastructure, using tools like Kubernetes, Docker, and CI/CD systems. And they're responsible for making sure models in production are versioned, traceable, and auditable. Their work ensures that what the data scientist builds and what the ML engineer deploys continues to work reliably, even as data changes, models drift, or systems scale. These roles aren't always neatly separated. In startups or small teams, one person might wear all three hats. In larger organizations, these roles become more specialized and collaborative. Data scientists ask the right questions and build the models. ML engineers build the infrastructure to serve those models. ML ops engineers keep everything running smoothly, automating and maintaining the entire lifecycle. Together, they form the engine behind any successful AI product. So, whether you're exploring a career path or building your own AI systems, understanding these roles is crucial. They each bring a unique set of skills to the table, but they also rely heavily on one another. If you're a data scientist, learn how your model fits into a larger system. If you're an ML engineer, deepen your understanding of model behavior. And if you're an ML ops, your work is what keeps the whole machine running. If you found this breakdown helpful, go ahead and hit that like button, subscribe to Let's Talk About Data, and drop a comment telling us which role you're most interested in or already working in. Now let's see, where is AI actually making an impact in the real world? Spoiler alert, it's everywhere. I'm going to take you through some fascinating, real-world applications of machine learning, examples you interact with almost daily, and others that are quietly transforming entire industries behind the scenes. Let's start with a quick refresher. Why use machine learning at all? Machine learning excels in situations where writing explicit rules or formulas would be too complex or downright impossible. Instead of giving a system step-by-step instructions, we feed it data, and it learns patterns, behaviors, and insights to solve tasks on its own. Think of ML as programming with data instead of logic. Let's begin with natural language processing, teaching machines to understand human language. Some examples: translation apps that convert speech or text between languages, voice assistants like Siri or Alexa, converting your voice into actions, spam filters that detect junk emails using learned patterns, sentiment analysis on social media or reviews to understand public opinion, text summarization and auto-generated replies, helping us save time and streamline communication. These systems don't just guess, they learn from massive amounts of text and become smarter with use. Now let's talk about computer vision, training machines to see and understand images. Real-world examples: image classification, figuring out if an image contains a dog, a tree, or a traffic light. Object detection, like spotting faces for unlocking your phone or identifying items in a self-checkout line. Medical imaging, detecting tumors in X-rays or CT scans, often with accuracy on par with expert radiologists. Semantic segmentation, used in autonomous driving to recognize roads, sidewalks, pedestrians, and more. Even artistic applications like AI-generated artwork, face filters, or turning photos into drawings. If you've ever seen a product magically tagged in an image or had your phone suggest a friend to tag, yep, that's ML in action. Next up, recommendation systems. Probably the most commercially successful use of ML. YouTube suggesting the next video, Spotify curating your playlist, Netflix picking your next binge, Amazon recommending a product before you even search for it. These systems learn from your behavior, compare it to millions of others, and optimize suggestions in real time. Without ML, personalizing content at this scale would be impossible. Even industries like fashion, yes, fashion, use ML. Some platforms combine AI and human stylists to send you clothes based on your taste and history. ML is also widely used in anomaly detection, especially in fraud prevention. Banks use machine learning models to detect unusual activity, flagging potentially fraudulent transactions in real time. And it's not limited to finance. Healthcare systems flag anomalies in patient data, manufacturing systems detect defects on production lines. Even cybersecurity firms use ML to monitor network behavior and detect threats before they cause damage. Now let's talk about reinforcement learning, where an agent learns by trial and error, improving its actions based on rewards. This is how AI beat the world champion at the game of Go. It's how robots learn to walk, grasp objects, or play video games with zero prior knowledge. It powers autonomous drones, robotic arms, and even smart thermostats that learn your preferences over time. These systems don't just follow rules, they adapt, optimize, and learn dynamically. And ML doesn't stop there. It powers predictive pricing in ride-sharing apps, automated loan approvals in fintech, dynamic inventory management in logistics, personalized education platforms that adjust lessons based on how you learn, even denoising and enhancing medical scans, improving diagnostic accuracy. Everywhere you look, from hospitals to highways, from smartphones to satellites, ML is working behind the scenes to make things smarter, faster, and more efficient. Machine learning isn't just a buzzword anymore, it's a foundational technology. It's helping us solve problems that were once considered unsolvable. It's enabling innovation across sectors and shaping the future of how we live,
Let's make predictions
and
evaluate
evaluate the model's
technology.
performance. If this video helped you understand how AI is transforming our world, drop a like, and don't forget to subscribe for more insights, tutorials, and real-world tech breakdowns right here on Let's Talk About Data. Got a favorite AI-powered app you use every day? Let me know in the comments. I'd love to hear from you. We just explored real-world applications of AI and machine learning. But here's the question: how do we actually go from a cool idea to a working ML product? Training a model in a notebook is just the beginning. In fact, it's only about 10% of the total workload. The real challenge lies in building, scaling, and deploying these systems into real environments. To make AI work in the real world, you need a complete workflow: problem framing, data collection, exploration, testing, deployment, and iteration. Let's break down the skills and tools you need to do this effectively. ML development isn't just about clever algorithms, it's about building reliable systems. That means writing flexible, clean code, avoiding duplication, refactoring relentlessly, and yes, testing. But technical excellence is only half the battle. The ability to communicate clearly, understand your users, and translate messy requirements into clean problems is just as critical. You need to listen, adapt, and guide, especially when bridging the gap between business goals and technical implementation. You can't solve a problem you don't understand. Every ML application starts by asking, what exactly are we trying to solve? What does success look like in the real world? Once the objective is clear, the next step is gathering the right data. Here, data exploration and visualization are key. You're not just crunching numbers, you're discovering patterns, judging quality, identifying biases, and engineering features that matter. Often, the biggest model improvements come not from better algorithms, but from better data understanding. Clean code isn't just nice to have, it's mandatory. Functions should be short, readable, and well-named. Control flow should be minimal and purposeful. Your codebase should be easy for others, and future you, to understand and maintain. Refactoring shouldn't be a one-time task, it's a continuous process. Keep things modular, don't repeat yourself, and most importantly, test everything. Bugs in ML systems can be subtle and costly. Speed matters. You'll rarely get it right on the first try. Start small, simple models, fast feedback, quick validation. Use prototypes to identify bottlenecks early and learn as you go. Being able to iterate quickly means tighter feedback loops and faster improvement. Let's talk about the actual tools that bring this all together. Jupyter Notebooks, great for experimentation, quick prototyping, and exploratory analysis. Scikit-learn, TensorFlow, PyTorch, core frameworks for building and training models. Pandas, NumPy, Matplotlib, essential for data manipulation and visualization. Flask or Fast API, useful for deploying ML models as APIs. Docker, enables reproducible, containerized environments, great for both dev and production. Git, version control is non-negotiable for collaborative, trackable work. S03, Redis, or local object stores, for storing and managing datasets and model artifacts. Monitoring tools, think dashboards and alerts. Once your model is live, you'll want visibility into performance and drift. Pipelines and MLOps platforms, automate training, validation, deployment, and versioning. These are especially helpful as your team scales and workflows grow complex. You don't need everything at once, but over time, these tools help systematize and scale your ML efforts. Building AI that works in production isn't about mastering a single model or algorithm. It's about combining deep problem understanding, software engineering discipline, and the right tools to ship something reliable, repeatable, and impactful. It's challenging, but it's what makes this field exciting. If this helped clarify what goes into real-world ML development, go ahead and like, subscribe, and drop your thoughts in the comments. Which of these skills or tools do you want to master next? I'd love to hear your take. We just broke down the core skill sets and tools that power machine learning applications. And we discussed one hard truth: training a model is just one small part of the real work. Now, we're zooming out to ask a bigger question. What's the future of AI engineering, and where should we focus our energy? Over the past decade, Machine learning has gone from academic curiosity to the backbone of real-world products, search engines, voice assistants, recommendation systems, you name it. But let's be clear, building a model is just the beginning. Turning that model into a scalable, reliable, and ethical product, that's a craft. That's AI engineering. AI engineering is about managing the entire lifecycle, from understanding the problem, collecting and preparing data, training, testing, and finally deploying it reliably. This is where MLOps becomes critical. The model might only take up 10% of the total workload. The real grind? Testing, versioning, validating, and making sure your ML product can survive in the wild. If you're thinking about the future, this is it. Full pipeline thinking, not just modeling. We're now seeing AI models with billions of parameters, trained across distributed systems using GPUs, TPUs, and advanced cloud platforms. The future engineer. Not just someone who writes code, but someone who can leverage massive compute infrastructure, optimize training, and scale deployment. If you're not cloud native yet, now is the time. Model architectures are evolving fast. What started with natural language processing is now expanding to multimodal systems that can handle text, images, audio, even control agents in robotics and gaming. Generative models, transformers, diffusion models, reinforcement learning, it's all moving fast. Staying ahead means not just knowing the buzzwords, but really understanding how and when to apply them. Despite all the shiny new tools, data is still the core of everything we do. If your data is bad, your model will fail, no matter how smart it is. Clean pipelines, versioning, validation, monitoring, all of this still matters and will always matter. Automation tools and pipelines will help you move fast, but they don't replace good judgment and hands-on understanding. Now, let's talk about what really matters, ethics. As AI becomes more embedded in society, questions around bias, fairness, accountability, and even misuse are front and center. AI engineering isn't just about performance metrics anymore. It's about building systems that are safe, fair, and transparent. That means diverse teams, responsible design, and critical thinking at every stage of development. So where are we headed? End-to-end pipeline ownership through MLOps, engineering for scale with cloud and distributed computing, mastering advanced multimodal AI architectures, never forgetting the foundation, data and automation, and always keeping our work ethically grounded. This is the roadmap. If you're building a career or product in AI, these are your pillars. The future of AI engineering is bold, fast, and full of impact. If this gave you clarity or inspiration, hit that like button, subscribe, and drop a comment. What part of the AI future excites or concerns you the most? Let's talk about it. Thanks for watching the first episode of AI Engineering Mastery. In the next episode, we'll dive into how to set up your AI engineering environment like a pro. Don't forget to subscribe, comment, and check out the Season 1 playlist. See you next time on Let's Talk About Data.